So let's start off with rewriting for the power rule, because that's the one that we do the most. Rewriting for the power rule, and we're going to have several different examples here. So let's start off with our first problem, which is going to be take the antiderivative of 1 with respect to x. Now, one of the things that you'll remember is that the derivative of x is 1. So when we're going back the other way, we just want to know what is the function whose derivative is 1. So here we're going to start off by rewriting this as the antiderivative of 1 and then x to the 0 power, because x to the 0 power just becomes 1. It's the same thing as it was right there. Notice I still have this antiderivative symbol. I haven't done anything yet. I'm just rewriting. Now when I go to take the antiderivative, I can use the power rule of saying I'm going to take this x to the 0, I'm going to add 1 to the exponent. So this 1 comes from 0 plus 1. And then I'm going to divide by my new exponent, which is 1. Always remember, when we take the antiderivative, that plus c comes along for the ride. So, if I get rid of my invisible 1's, there's my antiderivative. Now that we've started doing antiderivatives, we're always going to check our work by taking the derivative of x plus c, the derivative of x to the first power. When I bring down that 1, subtract 1 from the exponent, derivative of c is just 0. That's going to be 1. That's exactly what I started with. The next one we're going to do is a similar one. It's got those invisible numbers, so it sometimes trips people up. It's just the antiderivative of x with respect to x. And this one, likewise, we have that invisible number. I'm going to rewrite this as the antiderivative of x to the first power. When we take the antiderivative, we just add 1 to the exponent, divide by the new exponent, and add c. If we take the derivative to check our work, derivative of x squared is 2x, subtract 1 from the exponent, x to the first power is just x, and then this 2 is really just a 1/2. These cancel out. Derivative of c is 0, exactly what we started with. Some of the other rewrites that we'll do for the power rule are very, very similar to what we did for the derivative version of the power rule. So let's take the antiderivative of the square root of x dx. We remember from when we were doing the derivative that that's the same as x to the 1/2 power. And now this is just where you need to remember that now instead of subtracting 1 from the exponent, we're adding. So as we take the antiderivative, we take this, we start with 1/2, and then we add 1 to it this time. 1 is 2 over 2, so that's 3/2. So we have x to the 3/2, and then we divide by our new exponent, which is 3/2, and add c. When we're dealing with these fractions, make sure that you're comfortable with when we divide by a fraction. That's the same as multiplying by the reciprocal. So this is 2/3 x to the 3/2 plus c. To check our work, the derivative of 2/3 x to the 3/2 plus c. We've got the 2/3 along for the ride. We bring down the 3/2. Subtract 1 from the exponent, so that's 3/2 minus 2/2 gives us 1/2. Derivative of c is 0. And we end up with exactly what we started with. On a similar note, we can also rewrite the antiderivative of something with a negative exponent. Instead of x, I'm just going to use z I want you to be familiar with taking the derivatives with different variables and the antiderivative with different variables. Note that this variable here and this variable here must match. So if we have something with an exponent in the denominator, that's the same as just having a negative exponent, so 2z to the negative 3 dz. And now the 2 is just along for the ride, and we use our antiderivative rule to add 1 to the exponent. So this is z. Be really careful with this. This is negative 3 plus 1 is negative 2. Really, really tempting to make it negative 4 instead. And then we divide by the new exponent and add c. These 2's are going to cancel out. So we have negative 1. The z moves back to the denominator. There's an invisible 1 up top, plus c. When we take the derivative to check our work, this is the same as taking the derivative of negative 1z to the negative 2. And when we do that, we bring down that negative 2. Negative 2 times negative 1 is positive 2. Subtract 1 from the exponent, that's negative 3. Derivative of c is 0. And that's the same thing we had over here. Just make sure you don't make the same error if you make an error over here that you do over here, because then checking your work doesn't help you a whole lot. I want to show you one exception to this power rule where we're working with negative exponents, and it's a very, very important exception. So let's take a problem like this. We're going to do the antiderivative of 1 over x dx. And so let's try to do what would make sense. We're going to rewrite this as x to the negative first power, and we're taking the derivative there. And then what we're going to do is we're going to apply our power rule, and this is negative 1 plus 1, which equals 0. So that's x to the 0 power. And then we have to divide by our new exponent, so we have to divide by 0. Problem, we can't divide by 0. This is where there's a break in the power rule. This rule, antiderivative of x to the n dx equals x to the n plus 1 over n plus 1 plus c, only works when n does not equal negative 1. When we have this division by 0, and there's a problem with it. When you encounter this, you have to remember this. This is actually a memorized rule. The antiderivative of 1 over x is the natural log of x plus c. It's really tempting to do this instead, but notice that when you get to division by 0, that tells you, oops, I gotta remember that's the one number I can't do this rule with, and then you just have to go back to this and have that memorized. There's one final rewriting with the power rule problem that I want to show you, and this is actually rewriting with the constant multiple rule. And we've been doing this, I just want to make it really explicit. Let's just use t for our variable, just so we get used to working with different variables. The constant multiple rule just says that if we have 2 times, or a constant times, some other function, this is the same as that constant just being along for the ride. We can write it outside of this little symbol. So this is the same as saying 2 times the antiderivative of sine t dt. And it's not a really big deal for this particular problem, but sometimes it's going to be really handy just to sort of make the problem simpler that we're working with. So in this case, let's just finish this one off. To the antiderivative of sine, remember we're going the other way. Antiderivative goes the other way. Negative cosine of t plus c. And remember to check our work. The negative 2 is along for the ride, just like the constant multiple rule says. The derivative, though, of the cosine of t, so now we're going back the other way. Sine, cosine, negative sine, negative cosine. Cosine of t takes us back to negative sine of t. Derivative of c is 0. Negative times negative is a positive. That gives us positive 2 sine of t, which is exactly what we started with. Okay, now that we've done that sort of rewriting, let's look at a different sort of rewriting. This is rewriting to get rid of multiplication and division. Basically what's going on here, there is no equivalent for the product and quotient rules. There is an equivalent for the chain rule that we're going to get to in the next lecture, but if we have multiplication or division and we're trying to take the antiderivative, we're kind of out of luck. We have to rewrite it in order to be able to take the antiderivative. So let's look at a problem like this. Say we're trying to take the antiderivative of 3x squared plus 6x plus 4 all over 6x. And our variable is x. Well, there isn't a quotient rule when we're doing the antiderivative, so what we want to do is we want to rewrite this in a way that we can use one of our basic rules. And the easiest rule to use is that power rule. So if we have a rational expression, or a fraction basically, and we have one term down here in the denominator, we can basically split this up into several different terms and basically get this 6x to be under each one. The idea is that we know, for example, that if we have 1/3 plus 2/3, that's the same as 1 plus 2 over 3. And the deal is we can also go backwards. 1 plus 2 over 3 is the same thing as 1/3 plus 2/3. So we're just using that property to split this up. So this is the same as the antiderivative of 3x squared over 6x plus 6x over 6x plus 4 over 6x. And that's still all with respect to x. Now we can simplify these to make them into something that we can use the power rule on. 3 and 6 are both divisible by 3, so that's 1/2. Cancel out one of the x's. Anything divided by itself is 1. And then here we can reduce this, so these are both divisible by 2, so this is 2/3. X is in the denominator, so this is the same as x to the negative 1 power. Now, if you remember from up here, rewriting that as x to the negative 1 power isn't actually very helpful to us, because we can't use the power rule with it. So I'm actually going to undo this rewrite, because I'm catching that now rather than after I try the problem. And I'm going to still write this as 1 over x, because I know that the antiderivative of that is the natural log of x. So now I'm going to do my antiderivative step. This is the same as x to the first power. This is the same as 1x to the 0 power. So what I'm going to do is I'm going to bring the number along for the ride. This is 1/2. This is 1. We add 1 to the exponent, divide by the new exponent. This was x to the 0 power, so our new exponent is going to be 0 plus 1, or just 1, divided by 1. And this is 2/3, and the antiderivative of 1 over x is the natural log of x. All of that plus c. So what I'm going to get when I do this, multiply all this out, is I've got x squared over 4 plus, the ones are invisible, x plus 2/3 natural log of x plus c. This is very, very common if you have a function where you're splitting this up into multiple fractions or rational expressions. Typically you're going to end up with a natural log somewhere in the answer. That can be something that can kind of clue you in when you're looking at a multiple choice test. If you see a natural log, this kind of pattern in the answer choices, you might want to think about splitting up this rational expression. Let's go back and check our work. So the derivative of x squared over 4 plus x plus 2/3 natural log of x. So we bring down the 2, so that's 2x over 4. Derivative of x is 1. This is 2/3. Along for the ride, the derivative of the natural log is 1 over x. That's what we had over at this stage. So presuming that we did this correctly, there's not a really good way to check that we did this part correctly, but we can check at least that we did this part correctly. So this problem gets rid of division. Let's look at another problem for getting rid of multiplication. So let's say that we have a problem like this. We're doing the antiderivative of 4, let's do w for a change in variables, and all that's squared. Now what this really is, and this is in terms of w, what this really is it's 4w plus 2 times 4w plus 2. So we can't use the power rule right now because this isn't just like an x squared or a w squared. It's the box function, and we don't know what to do with box functions yet. But what we can do is we can expand this 4w plus 2, 4w plus 2, and get it into a form where we can just use the power rule. So that's 16w squared plus 8w plus 8w plus 4. So this is the same as taking the antiderivative of 16w squared plus 16w plus 4 with respect to w. Now when we take our antiderivative, we're going to add 1 to the exponent, so the 16's along for the ride. It's w to the 3rd divided by 3. Then the 16's along for the ride. We're going to add 1 to the exponent, that's an invisible 1. So 1 plus 1 is 2, divide by the new exponent. This is 4w to the 0 power, so we're going to bring the 4 along for the ride. 0 plus 1 is 1, so that's our new exponent, divided by 1, and then plus c at the end. So what we get when we simplify that is 16w cubed over 3 plus 8w squared plus 4w plus c. And when we check our work, when we bring down that 3, so we've got 16/3 times 3w squared plus bring down the 2, 2 times 8 is 16w plus 4, and that's what we ended up with here once those 3's cancel out. There are 2 final problems, and then there's an optional set of problems. So these sometimes show up. The antiderivative of the natural log of e to the 4x. Now for this one, we kind of know there's a trick because we don't really know the antiderivative of the natural log. I mentioned it to you, but it's not something we really work with. And so remember, natural log and e undo each other, so this is the same as the natural log of 4x dx. This is x to the first power, so the 4 is along for the ride. We add 1 to the exponent, divide by the new exponent, and add c. So we've got 2x squared plus c. Here, you got to make sure you do the simplification correctly, because our check step isn't going to get us back to there. It's only going to get us back to there. But we can take the derivative of 2x squared plus c. That's 4x. And that is indeed what we had there. So let's go ahead and end this section with the check for understanding. Let's do the antiderivative of x plus 1 squared over 3x, and that's all with respect to x. So try this one on your own, or restart the video when you're ready. Pause the video now. Okay, so we want to get rid of the multiplication and division so we can use our power rule. So let's start off just by doing this squared, x plus 1, x plus 1, x squared, plus x plus 1. So that means that this equals the antiderivative of x squared plus 2x plus 1 all over 3x with respect to x. And now we can go and split up our rational expression just like we did over number 7. So this is the same as the antiderivative of x squared over 3x plus 2x over 3x plus 1 over 3x, which is the same as the antiderivative. Let's see, one of these x's crosses out, so that's 1/3 x. These x's cancel out, plus 2/3. And then this is plus 1/3 times 1 over x. 1 times, if I multiply across, this is going to get me back to my original piece, so I'm just writing this 1 over x so that it's really clear to me what the antiderivative is going to be, that it looks like my rule. So let's go ahead and take the antiderivative. This is x to the first, this is x to the 0. So we add 1 to the exponent, that's x squared, divide by 2. 2/3 is along for the ride, we add 1 to the exponent, divide by the new exponent. The 1/3 is along for the ride, the antiderivative of 1 over x is the natural log of x, and we got plus c at the end. So our final answer is going to be x squared over 6 plus 2x over 3 plus 1/3 natural log of x plus c. We can check this doing the derivative of x squared over 6 plus 2x over 3 plus 1/3 natural log of x plus c. So this is 2x over, that's 6, 2x over 6 plus 2/3, this x, bring down the 1, that's x to the 0, which is just 1. And then plus 1/3, the derivative of natural log is 1 over x. So again, we have to make sure we did this right because it doesn't check that for us. But we will see this will simplify to 1/3, 2/3, and that's what we started with.